Hello there. So today we're going to analyze this beam by slope deflection method, and this is the first question that I am recording for the channel using slope deflection method. And this beam generally has two fixed ends, and there's a UDL from B to C along the span of B to C, and there's a point load at D along the span of A, B. So the first step to calculating a number in slope deflection is finding its fixed ends. And PSA, I do have flu, so my voice is a bit crusty and I might cough a lot, but pardon me on that, okay? Just going to calculate the fixed end moments, and you make sure that when you're calculating the fixed end moments, you should know what direction the moment is, okay? That's why you are able to see that the span of AB, when you're calculating the fixed end moment at AB, it's a negative, same as at BC. But then the fixed end moment of BA and CB is a positive. It's literally the same. I just didn't want to calculate it because I'm saving time, right? Then we're going to calculate the slope deflection equations. When you're calculating the slope deflection equations, you realize that in this question, the ends at A and C are all fixed end moments. They're all fixed ends, right? So when they're fixed ends, there's moment available. That means there's no equilibrium equation there. That equates the theta A and theta C to 0, since it's a fixed end. And then you're going to calculate the slope deflection methods as shown. But you should also take care and know that I know this formula, okay? That is something I'm not saying that you should cram, but I will do a more explanation on how this is derived in another video. Though right now, I just want us to go through this number because it's not even a hard number. I feel it's one of the easiest numbers, though it has two tricks that you should know here, right? The first one being the fixed end. The fixed ends having a moment available, making the equations 0. Then we're going to also calculate the equilibrium equations, and we have one joint in this number, and that's joint B. That means that the moments about BA plus the moments at BC will equate to 0. You get it? The summation at a joint is always equal to 0. You should have that at the back of your mind, right? So when you calculate this, we're finding the flexure. Sorry about that. We're finding the flexure rigidity, which is at this theta B, and we've found it as 17.2. So you substitute this 17.2 in all these equations that were numbered up here, and you find the respective moments. Okay, after finding the respective moments, it depends here on two people. If you're doing a paper, I would suggest, like for an examination, because I know structure analysis can sometimes take a lot of time, right? So I'm suggesting make sure to calculate immediately you've calculated the m values, draw the end moment diagram. You should draw it, and after drawing it, you also calculate the free moment. You should also plot the free moment diagram, because these values that you found here after the equilibrium equations can easily be used in the end moment diagram, and you can also calculate the free moment diagram values and you plot it. Thus you're going to save time, right? Instead of doing structure analysis number, which will be like for 30 to 45 minutes, if you use this method of immediately after finding the equilibrium equations and you plot the diagrams, you are more likely to save time compared to someone who is not immediately after the equilibrium equations, they start the support reactions. So you are more at an advantage. Instead of doing a number for 30 to 45 minutes, you're able to save some time and do this number for 20 minutes. You get it? And in case time elapses before you finalize the number, at least you're able to get marks up to here, which is a great achievement, because the support reactions are only going to help you in finding the SFD, which is the shear force diagram values, and you plot it, which I feel like is just time wastage. So do yourself the favor of finding the fixed end moments, then the slope deflection equations, equilibrium equations, end moment diagram, and the free moment diagram. make sure to do those two first, to do all this first. Then after that, you're going to plot the final bending moment diagram, which I've plotted it here and I've shaded it so well. That's when you now calculate the support reactions. And the support reactions, you're going to use the values that you found in the slope deflection equations to find each of their reactions at every point. After finding those reactions, you'll use them to find the shear force values. And those shear force values, my arrows, this is to represent after or which is at the right of A. And when I draw this, that is to represent the left or before that specific letter, okay? So you should know that. And then some people, instead of using the arrows, they might just write the word full, which I think is a good move. But as someone who wants to save time in her papers, I'm more likely to use the arrows. So after finding the shear force values, you use those values to plot the shear force diagram. So to end this video, I would like to inform you that I'm going to be doing more of slope deflection method questions. And I also hope to add some more of moment distribution, because those are the two main methods that I'm going to use in structure analysis compared to those other methods. But when I find time, I will also go into them, okay? But as I said, and using the specific flow in which I work this number necessarily doesn't mean you should only use it in slope deflection. You can do the same in moment distribution method. After you've manipulated the moment distribution table, you can immediately plot the end moment diagram, calculate the free moment diagram values, plot it, and the final bending moment diagram. Then you come for the support reactions. PSA, this is to save time, okay? Because it depends in the country you are in and in the curriculum, the way the curriculum goes. Because for me, in my university, we do 4 numbers for structure analysis. And when you do 4 numbers for structure analysis in a paper which is 3 hours, sometimes you panic and you don't think well. So to save time, at least use this method, this flow, the format that I use. So thank you for watching the video and have a great day.